Hello there, Mr. Sutton here, bringing you the AB Calculus 514 Extra Practice number 4 solutions on integration by substitution with indefinite integrals. On this problem, I notice that we have an inner function whose derivative, something with an x squared, is elsewhere here. So I'm going to try integration by substitution on this one. Let's let u equal this inner function of 2x cubed minus 1, and then du is going to be 6x squared dx. So then du over 6x squared will be our dx. Plugging things back in over here, we can write 24x squared times the square root of u, and then dx becomes du over 6x squared. 6x squared and 24x squared, we can get some canceling going on there. That leaves us with just a 4 and a u to the 1/2 power and a du. Using my reverse power rule, this exponent's going to bump up to a 3/2, multiplying by 2/3. That's going to be 8/3 out in front. So we have 8/3 u to the 3/2 plus c. And then plugging my u value back in there, we're going to put a 2x cubed minus 1 in for u and call it a day on this one. The key to integrating this expression is realizing that we have an inner function, e to the 3x minus 2, whose derivative, e to the 3x, is somewhere else in the problem. So we're going to use integration by substitution. Let's let u equal this exponent here, e to the 3x minus 2. Then we can say du is going to be 3 e to the 3x dx. And then dx is going to equal du over 3 e to the 3x. So substituting back into the original, we can write e to the 3x times 3e to the u power. And then dx, we were going to replace that with du over 3e to the 3x. So these 3e, well, the e to the 3x, this e to the 3x, and this one up here are going to cancel. We actually also get some canceling with this 3 and this 3. So when the dust settles, we just have e to the u du. And the derivative of that is e to the u plus c. And if you want, you can replace u with e to the 3x minus 2. On this problem, I notice that I have an inner function inside this 5th power whose derivative is somewhere else in the problem, so I'm going to try substitution here. Let me let u equal e to the 4x plus 3. Then du is going to equal the derivative of this, so 4e to the 4x, and then that 3 is just gone because it's a constant. Don't forget the dx. Dividing by 4e to the 4x, we get du over that stuff equaling dx. And now substituting back into the original, we can write u to the 5th. We still have the 12e to the 4x hanging around, and dx is now going to be du over 4e to the 4x. So let's see here. We got some stuff we can cancel. E to the 4x's are gone. 12 over 4, we can reduce that to 3. So we have 3u to the 5th times du. And then using my reverse power rule, this bumps up to a 6. 3 over 6 is going to give us 1/2 u to the 6th power plus c. And then we can just replace u with the expression that we substituted out for it, e to the 4x plus 3, to get our final answer. For this problem, instead of trying to distribute this out and expand this and do all that sort of craziness, we notice that there's an inner function here, 4x to the 5th minus 5, whose derivative, which is going to be something with an x to the 4th, is somewhere out here. So I'm going to try substitution. Let's let u equal 4x to the 5th minus 5, and then du is going to be 20x to the 4th dx. So we can say dx is really just du over 20x to the 4th. Plugging back in here, this is going to be 100x to the 4th times u to the 5th, and then dx is really du over 20x to the 4th. X to the 4ths are going to cancel. 100 over 20 gives us a 5 to go with our u to the 5th and our du. Using my reverse power rule, this 5 bumps up to a 6, so we end up with 5 over 6 u to the 6th plus c. And then don't forget to plug in the 4x to the 5th minus 5 for u, and there we are. For this one, we see that we have an inner function right here whose derivative is in the numerator, so this is a good one to try substitution on. Let's let u equal this e to the 4th minus 3 expression, and then we can say du, the derivative of all this, is going to be 4e to the 4x dx. So then dividing, we get dx equals du over 4e to the 4x. Plugging all this back in here, we can write 16e to the 4x over u to the third, and then dx is now going to be du over 4e to the 4x. Looks like these e to the 4x's are going to cancel, and 16 over 4 gives us a 4. We also have a u to the third down here, so I'm going to rewrite all this as 4u to the negative third du. Now I can use my reverse power rule. This exponent bumps up to a negative 2. Dividing by that, we have negative 2 u to the negative 2 plus c. And then substituting back in, we can write negative 2 times all of this stuff here to the negative 2 plus c. For this one, it looks kind of like a crazy mess, but the key here is recognizing that we have this inner function with an ln of 3x whose derivative, which is going to have an x in it, is somewhere else out here in the integrand. So I'm going to try some substitution and see what happens. Let's let u equal all this stuff inside, negative 3 plus ln of 3x. Taking the derivative of both sides, we can write du equals, and then this negative 3 is gone. Derivative of ln of 3x, that's going to be 1 over 3x times 3, so just 1 over x dx. Multiplying now, we get du times x is going to be the same as dx. And now substituting back in, we can write negative 2 cosecant squared of u, all that over x. And then instead of dx, we can write x du. The nice thing here is that these x's are going to cancel. So this is really just negative 2 cosecant squared of u du. And the derivative of negative cosecant squared by itself would just be cotan, or the antiderivative of that, I should say. So with the 2 there, this is going to be 2 cotan of u plus c. And then I'll substitute negative 3 plus ln of 3x back in for the u here to get this final answer. On this one, this looks really ridiculous with all these different trig functions in here, some of them nested in others. But one thing I do notice is that I have an inner function, cotan of 3x, whose derivative, which involves a cosecant squared of 3x, is somewhere else in the problem. So I'm thinking maybe if I try some u substitution, I might be able to get rid of a few things here. So let me give it a shot. Let's let u equal, we'll just go with cotan of 3x and see what happens. So du then, that's going to be negative cosecant squared of 3x times a tail of 3, so negative 3 cosecant squared of 3x with the dx there. And then dividing by that stuff, I can get dx by itself. All right, let's substitute some things back in. We still have a 12. We have a cosecant squared of 3x. And now we're going to have sine of u. And then instead of dx, we have du over negative 3 cosecant squared of 3x. Time to cross some stuff off. Cosecant squared of 3x, we will happily eliminate that. And then 12 over negative 3, that's going to be negative 4 to go with the sine of u and the du that are left over. Antiderivative of sine is going to be negative cosine. So this ends up being positive 4 cosine of u plus c. And then we can replace u with cotan of 3x to get our final answer. On this problem, I notice that I have an inner function, e to the 3x minus 2, whose derivative is elsewhere in the problem. So let's go ahead and use some u substitution on this. Let's let u equal e to the 3x minus 2. And then that means du, the derivative of all this, is going to be 3e to the 3x dx. And then we can say du over 3e to the 3x equals dx. Substituting back in, we still have this 3e to the 3x out in front. We have a secant of u, a tan of u, and then instead of a dx, we now have a du over 3e to the 3x. So a bunch of substituting happened there. It looks like this 3e to the 3x and this one down here completely cancel out, not even a non-1 coefficient left over, so that's kind of nice. So we're left with secant u tan of u du. Antiderivative of that is just secant of u plus c. And then we can plug in this e to the 3x minus 2 to get our final answer. For this problem, since there's no way to simplify this fraction, I look for other ways to deal with this. Now, one way to think about this is to think of this denominator as kind of an inner function. If you think about it that way, you'll notice that the derivative of this inner function, something with an x squared, is in the numerator here. So let's try a little u substitution and see where we can get with that. Let's let u equal 2x cubed plus 5. And then the derivative of that, we're going to have du equals 6x squared dx. So then we have du over 6x squared being the same as dx. Plugging back in here, we can now write 12x squared over u, and then instead of dx, we have du over 6x squared. X squareds are canceling. We also have 12 over 6, which is 2. So we have 2 over u, or 2u to the negative 1. Either of those. Either way, though, antiderivative is going to be a 2 ln absolute value of u plus c. And then replacing u with this stuff that has x in it, we can write 2 ln absolute value of 2x cubed plus 5, all of that plus c. For this problem, this is a little nuts, but I do notice that we have a function inside the e here whose derivative is also somewhere in the problem. So let me try u substitution and see what happens. Let's let u equal this 4x cubed plus 3 expression. So then we have du equals 12x squared dx, and then du over 12x squared equals dx. So now I can substitute for all the x stuff in the original, almost all of it. This 36x squared is hanging around for a little bit longer, but we can now write e to the u, and instead of dx, we can write du over 12x squared. X squareds are going to cancel. 36 over 12 is 3. We still have an e to the u du to go with that. Antiderivative of this is also 3e to the u, so that's kind of nice. Don't forget the plus c. And if we want to, we can replace that u with this 4x cubed plus 3 to get this final answer.